So, pleasure to be here. I really want to thank the organizers, to Eran, Shmuel, for the invitation. It's a lot of fun. It's an amazing workshop you've put together with also beautiful visit of the city, so thanks a lot, guys. And I wanted to tell Alan that in the back that you're not alone. I'm also a mechanical engineer by training with a primary appointment in civil engineering. So I don't know if it's better or worse, Alan, but I also talk about wiggles. And being in civil engineering in general, we break stuff, okay? And we look how things break. So we'll be talking a bit about breaking stuff, but at a small scale, trying to understand the debris level origins of adhesive wear, but trying to bridge, and we're not very successful yet, but trying to bridge to, let's say, engineering scale, macroscopic scales. So the main actor in what I will show today is Ramin, who is now a tenure track faculty in Denmark. Before I start my talk, I wanted to share one or two stories of Jay. So the good thing about being in Switzerland is that in the winter, when you have snow, it's quite easy to attract him to our shores to ski. And Jay loves skiing. So I've had the chance to ski with Jay. And I think we met around that time. It was a physics workshop in Les Houches in France, in the Alps. And the picture is not very good, but this is Jay. This is me, and you can see I'm wearing protections. I have a helmet. And I pride myself of being a decent skier. I've been almost, as a very young child, almost born on the slopes. And Jay is not necessarily as experienced. He has his own style, but he will go down any slopes. And I may be a bit faster than him, okay? But at the end of the day, and that's a picture of the end of the day, again, the quality is not really good, but I'm completely exhausted. You see no smile on my face. And Jay is still smiling, and he could keep going. He's absolutely relentless. He has a huge amount of energy, and you see this in his research. But I want to insist, maybe we've not talked about this enough, that he's also an athlete with a talent for running and an energy for sports in general. So it's been a lot of fun over the years, especially with Dave Kemmer, that has been my student, has done a postdoc with Jay. You've seen his name pop out yesterday a few times in Ilya's talk. And I must say, so I'm a numerical modeler. In my group, we do essentially numerical modeling. That's all what we do. And I must say that interacting with Jay, with his team, they are doing extremely complex experiments, but they are so clean and so beautifully monitored that for numerical modeling, it's absolutely pleasure, because when the experiments are well done, the numerical modeling can work and be helpful also for the experiments. So we share Dev in our academic genealogical tree. So I feel we are part of the same family, right?
But I was Dave's postdoc. Dave wasn't mine.
Okay. So we are part of the same family, and because we are in the same family, I can share some secrets. Every family has secrets. And I don't know if I should show this picture, but we've been, let's say 10 days ago in Amsterdam, Jay and I, and we were invited in a private party, and you can do pretty much anything you want to do in Amsterdam, right? And the Dutch, they don't do things halfway, right? So we were invited to wear a robe, and I want to show a picture of Jay in a robe. And he looks very, very good. So he's really a dynamic young man. I don't know if you have sandals under your robe, I forgot, but you look very, very good. Forever, forever young. Happy birthday, Jay. So although Jay does not wear, there's no sign of wear and tear, I want to talk about wear today, if I'm allowed to. And being in a holy place, being in Jerusalem, I wanted to show you this image of adhesive wear of St. Peter's statue in the Vatican. So I am told that it brings good luck to touch the right foot of St. Peter. And as you see, it seems like he's wearing a boot here, but really it's not. You should see toes like on the left foot. So the smoothing process comes through generations and generations of soft fingertips touching the foot of St. Peter. You see this dramatic process of wear. Now, wear is not only important for St. Peter statue, it's important for many, many, literally all engineering applications, or cars, planes. And so it's a very, very important topic. And I want you to read this quote from Ernest Rabinovich that is extracted from this book on friction and wear of materials. And for me, that's a Bible on wear. It's an extremely good book with a lot of very good information. And there's a description of many wear processes in this book. And what you return from this is that wear is a very dirty, a very messy process, an extremely complex process. So you have different type of forms of wear, including adhesive wear. That's when two asperities come together in close junction, they form adhesive bond, and then you may form or not a debris. You've got abrasive wear, when you scratch a hard material upon a soft material, and those are the most two important forms of wear. And then there's a lot of other types of forms of wear. And it's a very complex process because you form fur bodies, you have chemistry, you have a gouge being formed at the interface, the roughness evolves with time. It's just a complete mess, and it's not very well studied, I would say, from your point of view, from a physics point of view, with fundamental model experiments, because the life of a tribologist is really hard. It's just very complex to come up with model experiments. And the results of this, and I encourage you to read this paper, it's a very interesting paper that summarizes 50 years of research on wear, and it's basically a list of 300 equations that have been developed by the engineering community. Some of them with 26 material parameters and many more feed constants. So it's a pretty tough life, the life of a tribologist, right? And obviously, if you take one of those equations and apply it to a different set of conditions, humidity, you have to adjust the parameters, you have simply to throw away the equation and use another one, right? So I'm not going to go in my talk, between your coffee, I'm not going to go over those 300 equations, I reassure you. I'm just going to comment essentially one equation, so that's the only equation we're going to see in this talk, and I'm sure you can handle it as physicist. It's a very simple equation, and it's actually the most popular engineering adhesive wear model. It's called Archard wear equation. It's a model from the 50s, and it's very used in engineering because it's used to predict the lifetime of a mechanical component. So it tells you that the wear volume, and you measure this by collecting the pieces of debris that fall out of a contact, well, the wear volume is going to be proportional to the normal load, and there's data showing this. So it's linearly proportional, at least within a range of normal loads. It's linearly proportional to the sliding distance, so a usage life, and inversely proportional to the hardness. Okay? So we'll come back to this. The actually simple theoretical arguments you can use to come up with this. So that's a theory, that's a measurement. Forget about this. So you would like to have this perfect equality, but it doesn't work. So when it doesn't work, you have this magic factor called the K factor that you throw in the equation. And K is not a small adjustment. It's not 10% adjustment. It is more like a 6th order of magnitude adjustment. So K is a small number, 10 to the minus 8 to 10 to the minus 4, and no one really knows what is K. It's called the wear coefficient, and it can be only measured experimentally. It's usually interpreted as a probability. Surfaces are rough, and you form microcontacts here and there, and only a fraction of them, and in fact, if you take K to be 10 to the minus 6, a small fraction, say 1 per 1 million, will form a debris and will fall out of the contact. So it's interpreted as a probability. My long-term goal in life is to try to understand what is K. That's my question one. I will not really answer it today. I will tell you where we go along this way. Okay.
Just to help me do dimensional analysis.
Yeah, the dimensional
scale.
That's what it is. It's dimensional. Therefore, if you put in non-dimensional parameters, then maybe this K will be okay.
We'll go back to this, but that's the way it's done in experiments.
Yeah.
You have those two quantities. There's a K that must come out.
Because V is very small.
So it's interpreted as a probability. I want to point out that there exist beautiful experiments from the 60s showing the debris formation process at large scales. So this bar scale here is 2 centimeters with a measure of deformation, and you see this shear apparatus that's basically loading this triangular junction and forming a debris. We'll try to replicate this with atomistic simulations later. So more recently, there's been a lot of debate in the literature about the validity of Archard debris formation process when you go to nanoscale, based on very recent AFM atomic force microscopy experiments. So here I'm showing some data from a group in Switzerland, Gossman and Lanz, where you have this very sharp AFM tip that you drag along the surface, and the tip gets rounded. Okay, it smoothens, and you don't form a debris. So usually that's what you observe when you go to small sizes, when you have a very sharp AFM tips. And in fact, the contribution of Holm that preceded Archard in the 1940s got revived in the recent literature, where it was argued from Holm that when you form an adhesive junction, you will transform the mechanical work into plasticity, into plastic shearing, and a smooth transformation of a roughness. Occasionally, you do find AFM data where the tip breaks, and here you see a snapshot of this, where the tip is actually stuck due to van der Waals forces on the side of your FM tip. So occasionally, you do recover Archard description of adhesive wear. So you have those two different visions. So what do we have? What should we expect? Plastic flow, brittle fracture, Holm versus Archard? That's a second question. I will start by answering this. So what we hypothesize, what we put forward as a possible argument explaining the transition is in this paper here, is essentially a brittle to ductile transition, which can be explained fairly simply using energy balance, or Griffith's argument of a very simple geometry of a junction. Here you have two spherical asperities making a junction of size D, and we're going to load the system in shear. And as I increase my shear, I store more and more elastic energy. And the sigma j parameter is the strength of the junction, or it's a flow stress of the material. So up to sigma j, I can store any elastic energy, but above I cannot, right? And then I will start to have plastic flow. So that's my cap on the amount of elastic energy I have in this junction. So it's the elastic energy density. So G here is the shear modulus. It's a shear test, times the volume of material. Obviously, it's a very simplified geometry. We put a fudge factor alpha in front of it, but it's irrelevant for our discussion here. So that's Holm's mechanism, plastic smoothing. But if you have enough budget at the bank, enough energy budget, you can spend it on creating fracture. And here we assume we're going to propagate at the base of the asperities. So we know the total area that we need to break. It scales with the square of the junction size D. And the price to pay per unit surface is the surface energy I call S delta W. So if we look at this, how those energy terms change with the size of the junction. So this is D, the size of the junction, and this is the energy terms. My budget at the bank is the elastic energy. It scales with D cube. The price to pay to grow surfaces scales with D square. If I add those two curves, I get this green line, okay, that crosses over at a critical length scale D star. So below D star, we should expect that we do not have enough elastic energy. We should expect a smooth wear process. Above D star, we have enough budget, and we can grow cracks. So that's the expression of D star as function of material properties. It's really a material parameter. And we can compare this to a geometrical parameter, which is the size of a contact. OK, so that's what we've done with the AFM data we could put our hands onto. So this is an adhesive wear map, where this is a critical junction size. It's a material parameter. And if you pick, so here on this side, you have ceramics, and here you have metals. And there's a bunch of AFM data from literature for increasing tip size. So this axis is a aspirated tip size geometry. And when not reported in a paper, we try to estimate as good as we can what will be the area of contact between the FM tip and the substrate. And what we, in this line here is a crossover based on the critical length scale estimate from below this line, what should be a smooth wear, to debris formation. And you see data points that are in red. We chose the color red to express, to portray those data that did generate debris. And the black points show smooth plastic wear. So it's roughly consistent, okay, with the predictions. For metals, gold, silver. We are way below, the FM data we found is way below this transition length scale that we expect to be of the order of micrometers. We do have data from the 60s at scales way above centimeters, and this is a call for experimentalists to try to zoom on this area to see if we can maybe refine the estimations and our understanding for metallic junctions at micrometer sizes. So, okay, so this idea, in fact, we got it initially by doing molecular dynamics calculations. And it took us some years. What I'm telling you here today may seem very simple, but it took us some years, maybe because we're not that smart. But that's not the royal we, it's probably me who is not that smart. It took us some years to realize that when you do molecular dynamics simulations, you have a very small volume of materials, obviously, and you do get mostly ductile or smooth wear processes. Those are our calculations, for instance, a few years back, where you start with fractal rough surfaces, you slide it, and you're basically killing all the roughness. And again, the idea is this. It's very simple, is that if you look at the estimate of a process zone size at a crack tip, it's a big quantity from a molecular dynamics point of view. So this is an Ashby map of fracture toughness versus yield strength. And you can estimate the process zone size at a crack tip as a ratio of the fracture toughness of a yield strength to the square. And you see it's revealed here with those oblique lines, with those values. And for metals, it's big, millimeter sizes. Record MD simulations you can hope to do is basically a cube, micrometer cube. So we are way too big compared to molecular dynamics. Okay, ceramics, 100 nanometers, still big for molecular dynamics. So what we came up with is a new, very simple potential family that essentially makes us extremely brittle, to shrink the process zone size to values that we can hope to observe something on a computer. So essentially, we are as hard as diamond. Another interpretation of those model materials that I will not present today in details is to take this as a coarse-grained potential. So we are zooming out, and an atom is not an atom, it's a particle in my simulation that will print a group of particles, grains, so that we can hope to make parallels with rocks, okay? But I will not comment on this today. So this is our potential family. It's a very simple pair potential, repulsive tail, attractive tail. We can play with this tail to change the ductility, brittleness of our material. And we control two things. We have a control on the free surface energy and the unstable stacking fault energy, which is going to control the easiness of getting ductility, plasticity in our system. So you can see we have a good control of the hardness when we do indentation tests with this potential family. Now, we do not change the tail right at the origin. We only change this tail at 10% stretch so that we don't vary everything when we change the ductility. We want to keep the elastic constant, shear modulus, Young's modulus constant within a range of deformations that we can hope to understand something. Right. Okay, so the very simple calculations we've done look like this, although we are doing a bit more complicated now with multiple asperities. But initially we started with this, where we're going to have a collision between two asperities. The coloring is artificial. We maintain a fixed temperature. We're going to maintain the pressure constant. And because I maintain the pressure constant, the space will want to close, right? So in principle, the gap will close. But we're also going to shear repeatedly and see what happens. And we control the adhesive properties between the two bodies. We control the bulk properties, etc. So if we use a fairly ductile potential, and we pick a junction size that's going to be dictated by the geometry, those two asperities are going to collide, we're going to form a junction, and we're going to take it such that D is smaller than D star. So we expect Holmes mechanism. And that's what we get. So it's consistent with the theory. You see we've got some exchange of materials because there's adhesion. And because we maintain a constant pressure P, well, the space is closing, and at the end you form, let's say, a grand boundary. Okay? But if we pick D larger than D star, then a miracle happens where we see something very different, and we get Archard debris formation mechanism, and we got really, really excited about this. You form cracks, you form a debris that starts to roll, like what Zev may be seeing in rocks. you start to develop roughness naturally, although the surfaces were flat. And I think we have a lot of information to dig from there. So we have this transition at this star, and it's actually quite not extremely sharp transition, but there's a transition that we repeatedly observe for single asperity sliding test, 2 asperities in 2D, 3D asperities, those are much more expensive calculations, even including state-of-the-art diamond potentials, we also observe those things.
Does the volume continue to increase in both processes or only in the Brittle?
I'll discuss the volume in 2 slides. So this is very preliminary. I want to highlight one slide from a PG student, Enrico, whose goal is to understand the evolution of surface roughness. So initially, you start from very flat surfaces. There's going to be this collision. You're going to have large cracks, and you're going to form a large RMS roughness. But then there will be a running process, but it takes a very, very long time to see this running process emerge. And you have to develop techniques to extract the surface automatically. You don't want to do it by hand all the time. So you see this running process. And then I know there will be a talk by Amir this afternoon on surface roughness evolution in rocks. And this is not a very good plot here. But being here a physics committee in front of me, I have to say that we do observe scaling laws with some fractal behavior, h between 0.6 and 0.8, let's say. It's not very good, the image, but we have only 2 decades, unfortunately, of scaling. Why only 2 decades? Well, because those are very expensive calculations. We have only a small surface. So we hope to go to 3D. We hope to enlarge the system size. But we really want to understand what sort of exponent is emerging from the type of material properties we put in our system.
Why do you have only single debris?
In some cases, we can have double debris. And that's all. Here we have only a single debris because we have a single junction. Okay? But it turns out if we press harder, so we have a very narrow range where we have a single debris. If we have a large debris and we press hard, it will split and fragment. So we can, in some cases, obtain multiple debris. So we hope to keep working on this in the future. Well, in fact, as we speak. Okay, back to Archard wear law. I want to go back to this definition of K, which remains a mystery. So K is the small number interpreted as a probability of junctions forming debris. But now suddenly we become deterministic for K. Because what I told you so far is that there's this critical length scale or critical area of a junction above which you form a debris. So if your microcontact is too small, K is equal to 0 at the level of this microcontact. But if your microcontact is big, K is equal to 1. So we can start counting how many debris we get from a given rough surface. So let's pick a microcontact for which we know we are above this critical length scale. So K is equal to 1. And let's ask the question if the final volume of debris that is produced, is it proportional to N times S over H? Okay, is equal to this, not proportional. So if you go back to the 1953 Archard paper, there's a way to argue why you should expect this at the debris level. And the idea is very simple. So essentially, the volume of debris you form is going to be proportional to the cube of the junction size. So the wear rate, W, is the volume, proportional to d cube, divided by the sliding distance. And if you have a top view of a junction as you shear, the sliding distance scales with d. Okay, so you have d cube over d. So the wear rate should scale with the junction area, A, which is d square. And this junction area, if you have plastic flow, it's really the normal force over the hardness. So you simply get that the wear volume is N times S divided by H. That's the evolution of the normal force as a function of time or sliding distance portrayed in this Archard paper. Okay? So this is something we can do. We can measure this. What we control is those parameters. We control H, we control N, and we can measure the debris volume. And we do not find this proportionality from our data. And what you have here compiled is a 2D, 3D diamond type materials calculation. So we do not see this proportionality. It should not be, in fact, totally a surprise, because in Archard model, we assume there's a proportionality between a normal force and a real contact area, but we lose this here at the nanoscale because we have adhesive forces. So the fact that we have adhesion makes us lose this proportionality between contact area and N over H. We have also plastic shearing. So our junction, our contact duration is not the junction size, but there's going to be a plastic flow, a kind of a necking of a junction that you form. So instead, what works very well is this estimation from what we've seen, for the range of parameters we've seen, and we don't completely yet understand this dependency. We have some ways of interpreting it, but I think we have a lot more to do to understand. But what you see here is the integral of a tangential force ds over the junction strength sigma j. So it's the equivalent of Archard, but instead of taking a normal force over the hardness, you take the tangential force over the junction strength. And you see this force, tangential force, evolving with time in blue. The integral of this blue curve is this red curve, okay, as the debris forms. And this gives us a fairly, so this is a log scale, so there's a bit of spread, but still we get a fairly good, a good estimation of a debris of volume being formed. So we understand how big the debris should be, at least within a range of our atomic potential. Now, to go further than this, because it's very hard with atomistic potential to control a constitutive law. What we aim to do now is to go to macroscopic scale using finite element and continuum scale prediction with a phase field model to predict crack growth, plasticity, rate dependency. We need to put a lot more parameters to have a better fine-tuning of truly a predictive debris level adhesive law. So again, we have a scale dependence of n with A. At the macroscopic scale, of course, Archard is right, because you can neglect, from an engineering point of view, the influence of the adhesive forces. So you get this proportionality, Hamilton's first law between contact area, normal force, and tangential force. But as you go down in scale, this breaks down, and you lose this proportionality. So it's an adhesion control process. So this is a summary slide. So we have a new potential which permitted us to observe Archard debris formation mechanism to try to make baby steps in on understanding of wear. We have this critical length scale that explains, in our opinion, the transition between what can be seen at a small scale and a collision between large asperities at the engineering scale. The tangential frictional work predicts the debris size at the asperity level. We need to include interactions between debris, which we do not have at this point. And what we're trying to do, I'm not going to show this today, but we are doing mesoscale calculations, so boundary element method type calculations where we have large representative surfaces with lots of asperities at different length scales. And we can compute the distributions of contacts, of microcontact sizes. So we have statistics on this. And then we can just count, right? Count how many of them are above a critical size and come up with an estimate of K. And it turns out that experimentally, it's not obvious at all that K is independent of load. As you increase the load, you measure experimentally the same wear coefficient K. And why is that the case? Because the more I push, the more I will bring microcontacts, the more my microcontacts will grow. But we do find in BAM calculations that we have a range of loads for which K is indeed independent of load. And this we need to understand a bit further. Thank you for your attention.